In this video, we are going to look at differential equations. Sometimes, the rate of change is expressed in terms of the independent variable, and we are unable to directly integrate the expression. We will need to make use of a technique called separation of variables. In this video, we will learn how to do so with an example. A student has come up with the following equation modeling how a person learns. dy over dt equals 100 minus y, where y is the number of questions answered correctly in a proficiency test, and t is the time in years. What is a general solution to the differential equation? Unlike the previous examples that we have seen, the right-hand side of this equation is expressed in terms of y rather than t. However, we can still evaluate the equation by separating variables. This means that we move all the terms containing y to one side of the equation and all the terms containing t to the other side. This gives us 1 over 100 minus y dy equals dt. Next, we integrate both sides. After integration, we get minus ln 100 minus y on the left-hand side. We can find this by u substitution, or by observing that the derivative of minus ln 100 minus y is 1 over 100 minus y. The right-hand side is an indefinite integral of 1 with respect to t. Therefore, after integration, the right-hand side is t plus c, where c is a constant. We multiply both sides by minus 1 to get ln 100 minus y equals minus t minus c. We then exponentiate both sides. We get 100 minus y on the left-hand side and e to the power minus t minus c on the right-hand side. We can then separate the constant c from the rest of the power such that the right-hand side becomes e to the power minus t, e to the power minus c. Since its absolute value is always greater than 0, the right-hand side must be positive. Therefore, the constant e to the power minus c is positive. The expression inside this absolute value can be positive or negative. Therefore, 100 minus y equals plus minus e to the power minus c, e to the power minus t. We let d equal plus minus e to the power minus c, where d can be any positive or negative number. Therefore, we get de to the power minus t on the right-hand side. Rearranging this to make y the subject of the equation, we get y equals 100 minus de to the power minus t. Now, what is the solution when y0 equals 20? We substitute the initial conditions into the equation. This gives us d equals 80. Next, we substitute d equals 80 into the general equation. Therefore, y equals 100 minus 80 e to the power minus t. The graph of y is shown here. We can see that as t becomes larger, y gets closer to 100, and moreover, the rate of learning is greatest when t is small. The rate decreases as t increases. Now, let us consider some properties of the graph of the general solution. The graph on the previous slide hinted that there is a horizontal asymptote. What is the horizontal asymptote for the graph of the general solution? We know that the general solution is y equals 100 minus de to the power minus t. As t tends towards infinity, e to the power minus t tends towards 0. Therefore, y tends towards 100. The horizontal asymptote is y equals 100. This suggests that over time, a student's number of correct answers will tend towards 100. Is the differential equation a good model when the highest possible score is 150 and a person's initial score is 125? We substitute the initial conditions into the equation. This gives us d equals minus 25. Therefore, y equals 100 plus 25 e to the power minus t. The graph of y is shown on the right, and we can see that the test score decreases with time. The differential equation is not a good model because we expect proficiency, and hence test scores, to increase with time when a person learns. If the highest possible score on the proficiency test is 150, what might be a more appropriate differential equation to model a person's learning curve? The rate of learning is proportional to the amount of unlearned material. Moreover, the amount of unlearned material is proportional to the number of questions answered wrongly. Therefore, dy over dt is proportional to 150 minus y. We can write it as an equation dy over dt equals k bracket 150 minus y, where k is a constant. This differential equation is more appropriate when the maximum score is 150. If we solve this differential equation, we will find that the score tends to increase towards 150 over time for all initial scores less than 150. In the next two videos, we will look at more examples of differential equations.